In section 2.6, we begin the formal definition of continuity. And continuity, as you've probably discussed it in the past, is a function is continuous if you're able to draw that function without lifting up your pencil. But that's not much of a definition, and it sure isn't formal. Our definition of continuous is a function is continuous at any point on its domain if the limit as x approaches that function is equal to the function value. Now this says a whole heck of a lot in just this little statement here. What it says is, number one, it says that f of a is defined. Number two, it says that the limit at x approaching a of that function exists. And then it also says that that function limit equals the function value. In example 1, they want us to investigate a few places here where the function is not continuous. The function is not continuous, let's see, not continuous at x equal 1 first off. So we'll just say number 1, x equal 1. Why not? Because f of a doesn't exist, or it's not defined. f of 1 is what I should say. Not defined. Number 2, it is not continuous at x equal 2. The reason for this is number 3. Continuity checklist number 3 item is violated. The limit as x goes to 2 of our function equals, that limit equals 1, which is not equal to f of 2, which happens to equal 3. So this chunk does not equal that chunk. And that would be your reason. If asked to give a reason why the limit, why it's not continuous, you would need to state one of these reasons. That's why I'm modeling this behavior. You could also say, well, you couldn't say that it's not defined, let's say, and you can't say that the limit doesn't exist, because the limit does exist. At x equal 3, it doesn't work because, let's see, f of a is defined, it's there. The limit doesn't exist because in the neighborhood surrounding that x equal 3, they're not going, the left-hand limit does not equal the right-hand limit. So I will say limit as x goes to 3 of f of x does not exist. And number 4, x equal 5 is a place of discontinuity because, let's see, number 1, f of 5. Is f of 5 defined? Oh no, it isn't. That's a vertical isotope, so that is not defined. Okay. For example 2, I wanted to look at the graph and the tables for all of these so that I can get a better idea of what's going on. In example A, they want to know, is this function continuous at x equal to 1, or right here? I can see that it is not. And let's state why. If I look at the table for this function, which is over here, I see that that value, that function does not exist for x equal to 1. So for a, f of 1 does not exist. Therefore, f of x is not continuous at x equal 1. B is the same function, but they want to know what's going on at x equal to 2. I see that at x equal to, it looks to be continuous, and I see that there is not a hole, and that f of 2 does exist, and the limit is definitely going to be that same function value. So I'll say f of x is continuous, continuous at x equal 2, because the limit as x goes to 2 of f of x equals 17, which is equal to f of 2. This next function is defined in two pieces. It's defined as x sine of 1 over x, which I have graphed. I can see that for that function, x equals 0 is not defined, but they defined it in two pieces. They said, look at all of it except for where x equals 0, and when x equals 0, fill in that dot, fill in that hole, if you will. So there was a hole there, but it has now been filled in by this piecewise defined function. If that's the case, and that we have this piecewise defined function that's kind of filled in the gap, I can say that h of x is continuous at x equal 0, because the limit as x goes to 0 of h of x equals 0, which is equal to f of, fh of 0. And I think I did that over here. I called it f, and it should have been g. Excuse me. I'll fix it. So let me fix this one because it's really messy. Oops. Okay. H of 0. Note in these continuity rules, f and g are continuous at a, and that must be the case. F and g must be continuous at a for the following to hold true. So let's see what this means and see if we can figure out, if we can prove that, just say the first one is true, because the rest of them will be very similar to that. So if the limit as x approaches a of f of x equals some L, I know that that must also be the function value. Likewise, by stating that f and g are continuous at a, I know that this holds true of g of x must equal some, it doesn't have to be the same limit, so I'll just call it m of g of a. Alright, I know that this holds true. Therefore, I'd like to know about the limit as x goes to a of this combined f plus g. And I'd like to know what this would be. Well, I know that I can use the limit laws to say that the limit as x goes to a of f plus the limit as x goes to a of g. I know that this is equal to, we'll just say, some L plus some M. I also know that I could say that this is f of A plus g of A. And now I have all of the criteria necessary to say that it is continuous at the combined f plus g. And what I had to do was use those limit laws, so therefore it must be continuous because I can say that the limit as x goes to a of f plus g equals f plus g of a. And the rest of the proofs would just be similar to this. The next theorem wants you to expand it for a polynomial and rational function, and we've seen this happen time again. You can extend this technique for polynomials and rationals. The next thing they want me to do is for what values of this function is it continuous? Well, I can tell you where it's not continuous, and then that would let me know where it is continuous. So let me factor. X minus 3, x minus 4. I see that I'm going to have discontinuities at x equal 3 and x equal 4. So that means, if I look at a number line and know that at 3 and at 4 I've got these holes, I'll write this in interval notation. That means the function is continuous for any x in this interval from negative infinity all the way up to 3, not including 3. It's roundy guy bracket for that. Union with from 3 all the way up to 4 exclusively, not including those endpoints, or from 4 to infinity. If I wanted to write this in a different notation, I could have written it as such. This is a good notation. This is my interval notation. I could also write it as x is an element of the reals, meaning any real number where x is not equal to 3 or 4. Either way to write that, either like this or in this interval notation, is considered correct. Make sure you know that that's a roundy guy bracket. The next theorem has us look at the continuity of function composition. So I'm looking at f as my outside function and g as my inside function. And they say if g is continuous at some point a, and f happens to be continuous at f of g of a, meaning whatever that value is, then the function composition is also continuous. So let's look at what that might lead us to conclude. I'm going to look at this as f of x is going to equal x to the 10th. I'm going to look at it as g of x is going to equal that nonsense on the inside. So 4th minus 2x plus 2, x to the 6th plus 2x to the 4th plus 1. Because I have continuity and limit laws that deal with each of these individual parts, but I don't have I don't have a limit or continuity law that applies to this function as a unit. So let's look at the limit as x goes to 0 of just plain g of x. It appears this is a rational function, and I can just plug in that value 0 due to my theorem on rational functions and limits. So 0 to the fourth minus 2 times 0 plus 2 over 0 to the sixth plus 2 times 0 to the fourth plus 1 will yield 2 over 1, so that would equal a 2. I can see that g is continuous at a because the function value and the limit are the same. So I can state that. Let's look at the limit as x goes to 0 of f of x. This is just a plain polynomial. I can do a substitution of a 0. Sorry, I want 0, I want 2 because I'm looking at it as g of a. So I can plug that in. And this would be 2 to the 10th, or 1024. The limit equals the function value due to the fact that it was just a plain polynomial. Therefore, the composition of this function, 1024, is continuous.